Hello friends, in this video we are going to talk about yet another important function among all exponential functions is natural exponential function. So basically the theory of natural exponential function is derived from calculus. So in order to understand how this natural exponential function arises, we need to study the theory of limits. In particular, this natural exponential function is dependent on something raised to the exponent. That something is an irrational number that is called e, and I will make sure by the end of this video you will understand why this number e is very important. In particular, when we talk about number e, a ratio or a limit of some quantity is important, which is shown here. So from the theory of limits, it is known that whenever you are talking about 1 plus 1 upon n raised to n, this particular limit, it actually converges to e. So now unless you understand the concept of limits, you may not be able to have a complete understanding of this concept, but still I will give you some intuition behind this number e. Okay, so now as I mentioned earlier, the existence of e is actually studied in the field of calculus. For that you may have to do the course which is Math 2, Math for Data Science 2, and you have to agree with me on certain facts without knowing them, or you have to trust me that e is an irrational number and e is approximately equal to 2.71828 and so on. It's an irrational number, so it will go to never ending decimal representation. It will continue on the right. Okay, so these are the facts about e. Now the question that we asked at the beginning of the video is, why is e so important? So to answer that question, let us first look at the behavior of this particular number as a limit. So when I say that n grows without bounds, the number, this particular function f of n equal to 1 plus 1 by n raised to n converges to e. What do I mean? Let me put it in a proper formal way. So I have generated a table over here for our convenience, and let us understand. So when I substitute this n, the value of n, to be equal to 1, this number 1 plus 1 by n raised to n is simply 2. When I substitute n is equal to 10, the number becomes 2.5937. So does that mean this function will grow without bounds? The answer is no. That is why we get the convergence, and such type of questions are studied in calculus. So when you substitute the further values of n, that is n is equal to 100, you have substituted, you got 2.7048. when you substitute n is equal to 1000, you will get 2.7169. Now you can see that you are approaching closer to the ideal value of e. And when you put n is equal to 10,000, you get 7181. Still, because we are writing up to 4 decimal places, we are not really very close to it, but we are very close to it, but we are not at that point. But when I put n is equal to 1 lakh, then I get a value of e which is 2.7182, and that is actually exact representation of this number e up to 4 decimal places, correct, up to 4 decimal places. Now if you go on further and put higher and higher values of e, like you can put it to be a 1 million, 10 lakhs, and then you will see you will get further improvement. But because we are focusing only on 4 digits after decimal, this requirement is enough for us. This much calculation is enough for us. Another aspect in which this e becomes very crucial in accounts is interest rate calculations. You must have heard the term by now of continuous compounding, and continuous compounding actually means the taking ratios with respect to e, or taking exponents with respect to e. So let me demonstrate to you in this manner. Let us say you have invested rupee 1 in a bank, and bank is offering 1% interest rate. Okay, and you have invested it for 1 year. So in that case, what is the answer? 1 plus 1 upon 100 raised to 1. This is the answer, right? 1.01, 1%. You will get, if you have invested rupee 1, you will get 1 paisa of interest. Okay, so now if you go on like this, you will have something like 1 plus 1 by 100 raised to so whatever number of years you have invested in, raised to n. Now when you actually look at the procedure of the banks do not give you the interests which are given annually, but they credit the interest quarterly. So in that case, what you need to understand is the interest rate is actually given in a quarter. So it is computed on quarter, and whatever interest you have accumulated, that interest will be taken into account for the next quarter. So in that case, basically what bank is doing is, bank is taking this interest rate which is 0.01, and it is actually dividing it into 4 quadrants, 4 parts, because they are giving you a quarterly interest, and then you are actually getting this multiplied in this fashion. So here if you look at the interest rate, instead of 1 I have 0.01 as the number, and for 0.01 I got this number, right? So if the bank decides, okay, so I will revise the bank decides that I am revising, bank is revising the interest rate every month, then what will happen? Then the same logic for single year, remember 0.01 upon 12 raised to 12. Okay. So if the bank starts revising the interest rate infinitely often, right, then we are actually talking about something like 1 plus 0.01 by n raised to n, and this n tending to infinity. In this case, according to our judgment, according to this number was 1 here, now it is 0.01, and this number converts to e, right? So based on this understanding, if you apply the same logic and try to calculate this thing, then it will converge to e raised to 0.01. Okay. This is an interesting revelation. That means if you invest rupee 1, you just take that rupee 1 into e raised to 0.01, that will be the interest accumulated along with the original capital in your bank, if your bank follows continuous compounding. This is how whenever you study finance, you calculate the interest rate. Okay, so this is for the period of 1 year. Now if you add the period in terms of time, then it will be e raised to 0.01 t. So this is how e becomes important. Let us now replace this 1% by a generic number which is x. So what I am talking about now is 1 plus x by n raised to n. And now from the discussion that we have done, this will converge to e raised to x, and when I add the time, that is it is more than 1 year, then I have something like nt, and that is where I will get xt. Okay, so these are a simple understanding why the number e is very important. E typically comes when you are considering a continuous compounding. I hope I have made the relevance of the number e, irrational number e, very clear. And it is an irrational number, and its exact value is given by this particular expression. It's not exact, but it is approximate, which is suitable for our purposes. Now let us go further and understand what is a function that we have defined here, and it is why it is called natural exponential function. So this number e, as I mentioned now, naturally comes when you are considering continuous compounding. It also comes very naturally in the field of differential equations, which is also relying on our calculus. So this number E has a special name when you consider differential equations as an area, which is called Euler's number. So you can Google and you can search the meaning of Euler's number and why it is relevant. So that is how this E is called a natural exponential. Okay. So now let us formally define the function that we have just now seen, which is e raised to xt, as a natural exponential function. So a natural exponential function is defined as f of x is equal to e raised to x. Then you may ask a question, what are some interesting properties of this natural exponential function? Now the properties will be very similar to the exponential function that we have studied, but it is special in some sense. We will see its specialness when we will study some special properties of this natural exponential function e raised to x. Let us list all the properties. Domain of f, domain of this function, will be set of real numbers, and the range of the function is positive real line, that is 0 to infinity. As you have seen, the value of e is 2.7182, so e is naturally greater than 1. So if you recollect whatever we studied for exponential functions, you will get the graph of exponential function in this manner, where there are two typical points. 0, 1 is one typical point that it passes through, and it will always pass through 1e, right? As x tends to infinity, the function grows without bounds. As x tends to minus infinity, the function asymptotically goes to the x-axis. So y is equal to 0 is the horizontal asymptote for this function. We have already seen that. For general exponential function, same properties hold true. Now what makes e special, and what is something special that is not true with general exponential function? So in this case, if you look at the point 1 comma e, and if you draw a tangent to a line, tangent to the curve, that is a line passing through this particular point, the slope of this line will be e. That is very special. So e is the slope of the line that is tangent to the curve y is equal to e raised to x at 1e. So that is one thing. Then if you look at the area that is covered under this curve from minus infinity to 1, that area is actually e, the irrational number e. This you will learn when you will study calculus in math 2. So that is very important. And the third thing that is very important, which will not happen in general with other exponential function, is if you draw a curve f of x is if you draw a function f of x is equal to x, let me draw it. F of x is equal to 1 by x. So you may be familiar with that function. It will be something like this and something like this. Okay. And in this particular case, if you look at the area under the curve in the range 1 to e, this particular area, this area is a unit area for f of x is equal to x. And remember, this e is an irrational number, so still it will be a unit area. Why it is so? This is a matter of calculus to explore, but these are some of the things that makes the function f of x equal to e raised to x special function. Let us now understand this function better by considering an example which will deal with our real life problems. So here is an example which says that let R be the percent of people who respond to affiliate links under YouTube descriptions, and they purchase the product in T minutes, and that particular purchasing thing is a function of time. So it is given as the product RT is equal to 50 minus 100 times e raised to minus 0.2t. So let me give you a brief understanding of the problem. So now when you watch some video on YouTube, if you the speaker in the YouTube says that there are some affiliate links below in the description. Now if you click on that link and go to the affiliate site, then what you will do is either you will purchase or you will not purchase. If you will purchase, the speaker or the channel owner will get some amount of commission, right? Now here the person who is actually giving the affiliate links is interested in finding the number of people who are responding in T minutes. So he has devised a function which is available in YouTube statistics. So based on the data available, he has derived a function. We are taking his function as it is. So that function is RT, which is equal to e raised to 50 in minus 100 times e raised to minus 0.2t. Now he is interested in answering these questions. What percentage of people responding after 10 minutes? Okay. So how many percentage of people responded after 10 minutes? Then based on this function, what is the highest percentage expected? And the third question is, how long before RT exceeds 30%? The response rate being 30% is also a good enough rate, right? So because you are just putting some affiliate links. So let us try to understand what percentage of people will respond after 10 minutes. That means I want to essentially evaluate the function as R10. So if I substitute this, it will be 50 minus 100 times e raised to minus 0.2 into 10. That is simply, if you rewrite this as 50 minus 100 times, this is 2 by 10, which can be simplified to e raised to minus 2. And then you can actually calculate the function e raised to value of e raised to minus 2, and you can put the value. That value is 36.46. Okay, so this you can do it using calculator. Now let us look at the second question. What is the highest percentage expected? Now you have to think about this function, which is 50 minus 100 times e raised to minus 0.2t. Now you look at the function which is e raised to 0.2t or e raised to x. You already know the graph of the function which is e raised to x, f of x equal to e raised to x. Now how will the function look like when you are talking about f of x is equal to e raised to minus x? F of x is equal to e raised to x has a graph of this form, roughly this form. Now when you are talking about minus of x, you are actually taking a reflection of this graph along this, so that will give you some graph of this kind. Sorry, it will never cross x-axis, but it will go this way. Yes, so now you have an understanding of how the graph of e raised to minus t will look like. But here are some scaled versions like 100, this is 100 and this is 50. So now this graph is actually multiplied with minus 100. This graph is actually multiplied with minus 100, but multiplying with minus 100 will again, what it will actually keep the graph in a similar manner, but it will actually, because it is multiplied with minus 100, it will shift in some sense like this. 1 minute, let me, I have chosen an eraser. So it will shift like, it will flip here and it will shift like this. Okay, and then now when you are adding 50 to it, this graph will actually go up by 50 units. So this way the changes will happen to the graph, and final graph will look something like this. You can actually check for yourself. So basically first multiplying this minus sign will have an effect of reflecting the graph along y-axis, then multiplied with minus 100 will reflect the graph along x-axis, and then adding 50 will shift the graph by 50 units. So you have a fairly good understanding of the graph. Now you just apply your knowledge that what is the highest percentage expected. So in this case, if you understand this, the horizontal asymptote over here is actually shifted to 50 units because you are transferring to 50, and the graph actually, let me clear up the image. You can use your graphing tool also and verify that this is the graph. So the graph will look somewhat like this, and it will asymptotically reach to 50 units. Okay, so the highest percentage that is expected will be 50%. It will not exceed 50% based on the graphical analysis. Let us analyze this graph. Instead of graphically analyzing, let us look at this function e raised to minus 0.2t. This function in itself will never exceed 1, and as x tends to infinity, this function will actually tend to 0. That means whether I am multiplying by 100 or I am multiplying by 10,000, as t tends to infinity, this function has to go to 0. So this entire thing will go to 0, and therefore 50 is the maximum that I can achieve. Therefore my question B is answered as 50%. Okay. Now let us look at this particular thing, how long it takes before RT exceeds 30%. So in this case, you just look at the graph of the function. So as I have already described, this is how the graph of the function will look like. Now there are two ways in which you can solve, right? Let us try to see whether we can go ahead formally and solve this. So essentially I have been given that how long till RT exceeds 30%. That means RT is equal to 30. Find the value of t such that RT is equal to 30. So 30 is equal to 50 minus 100 times e raised to minus 0.2t. Okay, so 30 minus 50 will give me something like minus 20 equal to minus 100 times e raised to minus 0.2t. Now this is these minus signs will cancel themselves off, so this is this, it is this, and then you simply rewrite this expression. 20 by 100 is nothing but 1 by 5 is equal to e raised to minus 0.2t. Now I have to stop here because right now I don't have any ways to see what t will be when e raised to minus 0.2t is 1 by 5. No analytical way is possible. Then what I will do is, okay, so analytically I am stopping here, and if I somehow I am able to figure out how to find t is equal to something, then I can answer this question. But let us now try to compute this graphically. So in this case, RT equal to 30 is this point. So now if you go along this line and then you map this onto x-axis, remember x-axis is nothing but the values of t. So in this case, now you look at the mesh, this roughly turns out to be 8. That means t will be approximately equal to 8 minutes. So this is how we can, without even solving the expression for this, graphically solve the expression for exponential functions. So this is one live demo of that. Okay, that's all for now. So we will meet in the next video where we will actually try to understand how to solve this particular problem. Thank you.